Welcome. Today, we'll explore problem number 526, beautiful arrangement. This is a fascinating problem that challenges our understanding of permutations and constraints in combinatorics. We'll review the problem, discuss potential approaches, and analyze the solution step by step. Let's dive in. A beautiful arrangement is a specific way of arranging numbers from 1 to n such that a key condition is met for every position in the arrangement. The condition is that for any index I in the arrangement, either the number at position I is divisible by I, or I is divisible by the number at position I. The task is to determine how many such beautiful arrangements can be formed for a given integer n. The input to the problem is a single integer n, where n can range from 1 to 15. The output will be an integer that represents the total number of valid beautiful arrangements. This is the essence of the problem that we need to solve, and we'll now look at some examples to understand it better. For the first example, let's consider the case where n equals 2. The two possible arrangements of numbers from 1 to 2 are 1, 2, and 2, 1. Both of these arrangements satisfy the conditions for a beautiful arrangement. In 1, 2, the first number, 1, is divisible by its index, and the second number, 2, is also divisible by its index. Similarly, in 2, 1, the first number, 2, is divisible by its index, and the second index, 2, is divisible by the number at that position, which is 1. Since both arrangements meet the criteria, the output for n equals 2 is 2, meaning there are two beautiful arrangements in this case. In the second example, we have n equal to 1. When there is only one number, the only possible arrangement is 1. Here, the condition is naturally satisfied because the number 1 is divisible by its index, which is also 1. Since there is only one valid arrangement, the output for n equals 1 is 1. This example demonstrates the simplicity of the problem for the smallest input value. Now, let's take a look at the constraints of the problem to better understand the scope of possible inputs and outputs. The constraints for this problem specify that n will always be between 1 and 15, inclusive. As n increases, the number of possible arrangements grows factorially. For instance, when n is 2, there are 2 factorial, or 2, possible permutations. When n is 3, there are 3 factorial, or 6, permutations, and for n equal to 15, there are 15 factorial permutations, which is a very large number. While the problem involves considering all these permutations, the divisibility conditions allow us to filter out invalid arrangements efficiently using techniques like backtracking. Some key edge cases to consider include the minimum input, where n equals 1, and the maximum input, where n equals 15. The algorithm must handle these extremes as well as general cases where n falls anywhere in the given range. Finally, it's important to highlight the non-trivial nature of the conditions that the algorithm must check. For each index in the arrangement, the algorithm needs to verify that either the index is divisible by the number at that position or the number at that position is divisible by the index. Both conditions must be accounted for at every step to ensure only valid arrangements are included in the final count. This requires careful implementation and efficiency, especially as n grows larger, to handle the increasing number of permutations effectively. To solve the beautiful arrangement problem, let's first consider the brute force approach. The idea here is to generate all possible permutations of numbers from 1 to n. For each permutation, we check if it satisfies the problem's conditions, that is, for every position I, either the value at that position is divisible by I plus 1, or I plus 1 is divisible by the value at that position. While this approach is straightforward, its inefficiency becomes apparent as n increases. Generating permutations involves a factorial growth of possibilities, which is computationally expensive. Additionally, verifying each permutation takes linear time, resulting in an overall time complexity of O(n). (n). The space complexity is linear, as we need to store the current permutation during recursion. However, this approach has significant drawbacks. It performs unnecessary computations by exploring all permutations, even those that clearly don't meet the conditions. This inefficiency makes it impractical for larger values of n. A more refined method is the backtracking approach, which systematically builds valid arrangements. By placing numbers in valid positions one at a time, we can prune invalid paths early, avoiding the need to generate and check all permutations. At each step, we select an unused number and verify if it satisfies the divisibility condition for the current position. If it does, we proceed; if not, we backtrack and try another option. The key insight here is that the condition for a position depends only on that specific position, allowing us to skip unnecessary computations. Additionally, by tracking used numbers, we avoid redundant work. This drastically reduces the search space, making the backtracking approach far more efficient than brute force. Its time complexity is proportional to the number of valid arrangements, which is significantly smaller than n. For larger values of n, and its space complexity remains linear due to the recursion stack and a tracking array. Another advanced method to solve the problem is dynamic programming combined with bit masking. This approach uses a bit mask to represent which numbers are still available for use. Each bit in the mask corresponds to a number, where a set bit indicates the number is already used. Additionally, a DP array, DP mask, is used to store the number of ways to form valid arrangements for the given mask. The transitions between states are defined recursively. For each position I in each available number, we update DP mask by adding the count from DP prev_mask, where prev_mask excludes number. This update is valid only if the divisibility conditions, number %I = 0 or I %number = 0, are satisfied. The time complexity of this approach is 2 to the power of n asterisk n, as there are 2 to the power of n subsets of numbers, and for each subset, we iterate through n numbers. The space complexity is 2 to the power of n, due to the DP table. While this method can be theoretically optimal, it is more complex to implement compared to backtracking. Handling the transitions between bit masks requires careful attention, and debugging can be challenging. As a result, although this technique is powerful, its complexity makes it less appealing for smaller input sizes where simpler approaches may suffice. Among the discussed strategies, backtracking was chosen for this problem because it offers the best balance between simplicity and efficiency. While dynamic programming with bit masking provides a theoretical advantage, its implementation is significantly more complex and doesn't lead to a noticeable performance improvement for smaller values of n. On the other hand, backtracking avoids the factorial growth of brute force by pruning invalid paths early and directly building valid arrangements. This makes it computationally efficient while remaining intuitive to implement. Comparing the approaches, brute force is the simplest conceptually but quickly becomes infeasible due to the factorial explosion in permutations. Dynamic programming with bit masking, although optimal in theory, is harder to code and debug, requiring careful handling of state transitions. Backtracking, however, strikes a perfect middle ground. It leverages pruning to avoid unnecessary computation, is straightforward to implement, and aligns well with the problem's constraints. This makes backtracking the most practical and natural solution for the beautiful arrangement problem, providing clarity without sacrificing efficiency. To solve the beautiful arrangement problem, the goal is to find all valid permutations of numbers from 1 to n that satisfy specific divisibility conditions. For each index I, either the number at that index is divisible by its one-based position, or the position itself is divisible by the number. We start by generating all possible permutations of numbers from 1 to n using a backtracking approach. This ensures that we explore every possible arrangement. Once we have a permutation, we validate it by iterating through all indices and checking if the divisibility conditions are satisfied for each index. If a permutation meets these conditions for every index, it is deemed valid. This brute force method guarantees correctness, as it systematically checks every arrangement of numbers. After validating a permutation, we store it in a list of valid permutations if it satisfies the given conditions. Once all permutations have been processed, we return this list as the final result. While the approach is straightforward, it can be computationally expensive due to the factorial growth in the number of permutations. To mitigate this, we can optimize the process by pruning invalid branches during the permutation generation. The key to this problem lies in understanding the divisibility constraints. These conditions establish a relationship between the value at an index and its position, allowing us to eliminate many invalid permutations early. Backtracking is particularly effective here, as it systematically explores all possibilities while pruning paths that violate the constraints, reducing unnecessary computation. When considering edge cases, the problem behaves differently depending on the size of n. For small values like n equals 1, there is only one permutation, which is always valid. However, as n grows larger, the factorial growth of permutations makes a brute force approach infeasible without optimizations like pruning. In terms of data structures, we use a list to dynamically build the current permutation during backtracking. Lists are ideal here because they allow efficient appending and removal of elements. Additionally, we use a set to track which elements have already been included in the current permutation. Sets are useful because they provide constant time checks for membership, ensuring that numbers are not repeated within a permutation. The time complexity of this approach is n*n, since we generate all n. Permutations invalidate each one in n. Space complexity is dominated by the storage of permutations, which is n, in the worst case. The backtracking process requires additional space proportional to n for storing the current permutation and tracking used elements. Let's walk through an example with n equals 3. First, we generate all permutations of the numbers 1, 2, and 3. These permutations include 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Next, we validate each permutation against the divisibility conditions. For instance, 1, 2, 3 is valid because it satisfies the constraints at every index. Similarly, 1, 3, 2, 2, 1, 3, 3, 1, 2, and 3, 2, 1 are valid, but 2, 3, 1 is invalid because it fails the conditions at one or more indices. The final result includes all valid permutations. Optimizations such as pruning invalid branches during generation and using iterative algorithms like Heap's algorithm can further improve efficiency by reducing the overhead of recursion. Here is the Python implementation of the algorithm. The function generate_permutations takes an integer n as input and uses a backtracking approach. Inside the backtrack function, we recursively build permutations by adding numbers from 1 to n that are not already used. When the length of the current permutation reaches n, we check if it satisfies the divisibility conditions. If it does, we append a copy of the permutation to the results list. After checking, we backtrack by removing the last number and marking it as unused. This ensures that all possibilities are explored systematically. The results list is returned after all valid permutations have been generated. For example, if we call a function with n equals 3, it will output all valid permutations 1, 2, 3, 1, 3, 2, 2, 1, 3, 3, 1, 2, and 3, 2, 1. This implementation highlights the elegance of backtracking and solving combinatorial problems efficiently. This solution defines a function count arrangement inside the solution class. The problem is solved using backtracking. The idea is to recursively try to place numbers into positions from 1 to n while ensuring the constraints of the problem are satisfied. The backtrack function takes two arguments: index, which represents the current position being filled, and visited, a Boolean array that keeps track of whether a number has already been used in the arrangement. If index exceeds n, this means all positions have been filled, so we return 1 to count this valid arrangement. Within the recursive function, we iterate through all numbers from 1 to n. For each number, we check if it satisfies the condition: either the number is divisible by the current index or the index is divisible by the number, and if it hasn't already been used. If both conditions are met, we mark the number as used by setting visited number to true, recursively call backtrack for the next index, and then backtrack by unmarking the number visited number equals false. The visited array is initialized with false for all numbers at the beginning of the function, and the recursion starts from index 1. The result is the total count of valid arrangements, which is returned by the function. This approach ensures that all valid arrangements are explored and counted, and the use of backtracking avoids unnecessary computations by pruning invalid states early. The algorithm is efficient for small to medium values of n and leverages the constraints to reduce the search space significantly. This is the Java implementation for LeetCode problem number 526, beautiful arrangement. The solution uses backtracking to explore all possible arrangements of numbers from 1 to n. A Boolean array is used to track which numbers have been visited. The key conditions for a valid arrangement, index percent number equals 0 or number percent index equals 0, are checked before proceeding with recursion. The implementation mirrors the Python logic closely, with type declarations and Java-specific syntax adjustments. The problem we're solving is called beautiful arrangement, where we need to count all valid permutations of numbers from 1 to n. Each permutation must satisfy a specific condition for every index I in the arrangement. Either the number at position I should be divisible by I, or I should be divisible by the number at position I. To tackle this problem, we use a backtracking approach. The idea is to explore all possible arrangements recursively while enforcing the given constraints at every step. Let's start with an example where n equals 2. In this scenario, the input size is small, making it easier to illustrate how backtracking works. We initialize a visited array, which helps us keep track of which numbers have already been placed in the arrangement. This array is indexed from 1, so for n equals 2, we start with false, false, false. Initially, the backtracking process begins at index equals 1, where we try placing each number that satisfies the conditions for this position. At index equals 1, we have two choices: place the number 1 or place the number 2. First, we try placing 1. The condition is satisfied because 1 is divisible by 1. We mark 1 as visited, updating the visited array to false, true, false, and then move on to the next index. Now, if we place 2 at index equals 1 instead, the condition is still satisfied because 2 is divisible by 1. This updates the visited array to false, false, true, and we proceed to index equals 2. At index equals 2, we recursively evaluate the remaining numbers. If 2 is placed at index equals 1, we can only place 1 at index equals 2, and the condition is satisfied because 2 is divisible by 2. This gives us a valid arrangement, and we reach the base case since all indices are filled. Similarly, if 1 was placed at index equals 1, we can place 2 at index equals 2, satisfying the condition. By the end of this process, we find two valid arrangements, 1, 2, and 2, 1. Now, let's consider a slightly larger example with n equals 3. Here, we begin with the visited array initialized to false, 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 and start our backtracking from index equals 1. At this index, we have three options: place 1, 2, or 3. First, placing 1 satisfies the condition because 1 is divisible by 1. We mark it as visited, updating the array to false, true, false, false, and proceed to index equals 2. Similarly, placing 2 at index equals 1 satisfies the condition, updating the array to false, false, true, false. Lastly, placing 3 also satisfies the condition, updating the array to false, 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 true. For each of these placements, we continue backtracking to the next index, ensuring the constraints are met at every step. At index equals 2, we continue exploring valid placements for each branch. For example, if 1 was placed at index equals 1, we can try placing either 2 or 3 at index equals 2, as long as the conditions are satisfied. Similarly, if 2 is placed at index equals 1, we can try placing either 1 or 3 next. Finally, if 3 was placed at index equals 1, the remaining options are 1 or 2. At index equals 3, we complete the process by placing the last remaining number, ensuring that the constraints are still satisfied. Each time we reach the base case, where all indices are filled, we count the arrangement as valid. By exploring all possible branches using backtracking, we find that there are 3 valid arrangements for n equals 3. This systematic approach works efficiently for small values of n because backtracking allows us to prune invalid branches early. The visited array helps ensure numbers are only used once in each arrangement, and the constraints are dynamically applied at every step to prevent invalid placements. The time complexity of our solution is driven by the backtracking approach, which systematically explores all valid permutations of numbers from 1 to n. To understand this, we can break it into 2 parts. First, the number of recursive calls made by the algorithm. At each index, the algorithm considers all unused numbers that satisfy the given conditions. Either the number is divisible by the index or the index is divisible by the number. In the worst-case scenario, all numbers are valid at every step, leading to n possible permutations. This means the number of recursive calls is bounded by n factorial. Second, the work done within each recursive call. Here, the algorithm iterates through all numbers from 1 to n to check whether they can be placed at the current index. This requires O(n) operations for each call. When we combine these two factors, the overall time complexity becomes O(n) multiplied by O(n), which simplifies to O(n*(n). Now, let's analyze the space complexity of the solution. This is primarily determined by two factors. The first is the recursive call stack. Since the depth of the recursion tree corresponds to the number of indices, or n, each recursive call adds one frame to the stack. Therefore, the space used by the call stack is proportional to O(n). The second factor is the visited array, which is used to track which numbers have already been placed in the arrangement. This array has a size of n+1, requiring O(n) additional space. When we combine these two components, the total space complexity is O(n) for the recursive stack plus O(n) for the visited array, resulting in an overall space complexity of O(n). Let's compare this backtracking approach to a brute force method. A naive solution would generate all n permutations of numbers from 1 to n and then verify if each permutation satisfies the conditions. This brute force approach would require O(n) time because it not only generates all possible permutations but also validates each one. In contrast, backtracking improves efficiency by pruning invalid branches early, skipping unnecessary computations. However, despite these optimizations, the time complexity of backtracking in the worst case remains O(n), because it still has to explore all valid permutations when all numbers are valid at every step. In the best case scenario, the algorithm might terminate early if most numbers are invalid at certain steps, but this is highly input dependent. On average and in the worst case, the algorithm must traverse most or all of the recursion tree, maintaining the O(n) complexity. Mathematically, the exponential nature of the problem becomes clear when we consider the growth of n. The number of permutations increases factorially with n, and this dominates the overall time complexity. While there is linear work done at each level of recursion O(n) operations to check valid numbers, this linear factor is negligible compared to the explosive growth of the recursion tree. This ultimately gives us an overall time complexity of O(n). In conclusion, while our backtracking approach is significantly more efficient than brute force by avoiding redundant computations, the problem remains inherently combinatorial. The exponential growth of the recursion tree limits the scalability of the solution as n increases, making it efficient only for small values of n. When solving problems like beautiful arrangement, there are several common mistakes to watch out for. One of the most frequent issues is not accounting for edge cases, such as when n equals 0, 1, or when you're dealing with very large constraints, like n being 10,000. These edge cases often expose hidden bugs or inefficiencies in your solution, so be sure to test thoroughly. Another mistake is using inefficient data structures. For example, if you're checking for duplicates, using a list instead of a set can unnecessarily increase the time complexity from O(n) to O(n²). Choosing the right data structure can make a huge difference. Similarly, beginners sometimes overcomplicate their solutions by trying to apply advanced techniques like dynamic programming, even when simpler approaches, such as sorting or greedy methods, would suffice. Overcomplicating doesn't just waste time, it makes debugging harder too. Finally, ignoring constraints or assumptions provided in the problem, like a sorted input, can lead to suboptimal solutions. Constraints often give important hints about how to optimize your approach, such as using binary search for sorted data. Premature optimization is another pitfall to avoid. Jumping directly to a complex approach without first validating the brute force solution can lead to errors and misunderstandings about the problem. A good practice is to always start with the simplest brute force solution to ensure correctness before optimizing. This is especially important in interviews, where demonstrating your thought process is key. Speaking of interviews, it's a good idea to begin with a brute force approach to show you understand the problem. Even if it's not efficient, it provides a foundation to build upon. As you discuss optimization, make sure to highlight the trade-offs between time and space complexity for each approach. For instance, compare how a greedy method reduces space complexity compared to dynamic programming. Look for patterns in the problem, such as monotonic sequences, prefix sums, or sorted input, since these often lead to natural optimizations. While coding, make your thought process clear by verbalizing each step. For example, you might say, I'm iterating through the array to find the largest element, which is O, n, and then explain the next step from there. To deepen your understanding of related problems, you can practice with similar challenges. For instance, LeetCode 46 focuses on generating permutations, making it an excellent exercise for backtracking. LeetCode 39, combination sum, is another great problem that involves exploring all combinations that meet a condition, which is similar to working with permutations. LeetCode 47 builds on permutations but introduces the additional complexity of handling duplicates. Finally, LeetCode 31, next permutation, is about efficiently generating the next lexicographical permutation, a skill that overlaps with permutation-based problems. Now, let's talk about alternative approaches you can use. Brute force is the most straightforward method. Generate all possible solutions and check if they meet the conditions. While simple and guaranteed to provide correct results for small constraints, it quickly becomes impractical due to its exponential time complexity. Backtracking is a systematic way to explore subsets of solutions, applying constraints as you progress. It's more efficient than brute force in constrained problems, but it still has exponential complexity in the worst case. To optimize backtracking, pruning unnecessary branches is crucial. Greedy algorithms are another alternative, where you make locally optimal choices at each step. These often reduce complexity to O, n, or O, n log n, but they only work for problems that allow this approach, which requires careful insight. Dynamic programming is another powerful approach to consider. This method involves breaking the problem into smaller, overlapping subproblems and solving them efficiently using memoization. Unlike brute force or simple recursion, dynamic programming avoids redundant computations, making it a great choice for problems with overlapping subproblems. However, it does come with its trade-offs. Dynamic programming often has higher space complexity due to the need for memoization tables, and it can be harder to implement under time constraints. Mastering this technique requires practice, as understanding how to define the state transitions and memoization structure can be tricky. That said, dynamic programming is one of the most versatile and effective tools for solving complex computational problems when applied correctly. Great job! In this session, we covered the beautiful arrangement problem, explored different approaches, and highlighted the importance of backtracking and constraint optimization. Remember, practice makes perfect, so keep challenging yourself with similar problems. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!